My name is Vaibhav Savant. I'm with the LIGO India EPO team, and as part of the Vigyan Samagam event that we are having here, we are very pleased to have Devnandini Mukherjee, who is a postdoctorate fellow at IIT Bombay. So, welcome Devnandini. Devnandini completed her PhD from Wisconsin.
Okay, so I completed my PhD in May 2018, it's last year, from University of Wisconsin at Milwaukee in the US. And okay, so I'll just introduce myself.
I'll just get started right away since we are running late, so I'll let her introduce herself.
Okay. Can you switch on the mic? I will just. Yeah, while that's being figured out, let me introduce myself. So as you just heard, I'm a postdoctoral fellow at IIT Bombay right now, and I did my PhD last year. And as you may have guessed, I work with the LIGO Virgo collaboration. And so I have been working on compact objects and looking at the mergers or coalescences of compact objects. And I especially focus on the heavier mass compact objects. And we look at gravitational waves coming from such mergers. And I'm going to give you a brief update of the various things we have seen using gravitational waves so far and what the future might hold for us. So let me see if everything works here. Okay. Okay, so just to give you a brief summary of what we are going to do in the next 45 minutes or so. So I'm going to start with a brief introduction to the Laser Interferometer Gravitational Wave Observatories, or the LIGO observatories as they are acronymed. And then I'm going to briefly talk about some of the things that we have seen so far and what we have been learning from this kind of science. Then I'll give you a very small sneak peek into how exactly we analyze the data from these detectors and how the behind the scenes work goes. And then I'll give you a brief idea about some of the ongoing and future work. So let me begin at the beginning, as they say. So back in the year 2015, on the day of 14th of September, back when I was a fourth year PhD student and I was all naive, I heard that humans had picked up something from space that was going to change the history of astrophysics forever. And no, I'm not talking about picking up signs of aliens yet, but even better. You'll see. So, I don't know what I did. Okay. So, let's try and play this video. Okay. I don't think the videos play from here. Okay, so this is a simulation of what really happened in terms of that event. So two black holes, almost as large as 30 times the mass of our present sun, were seen in spiraling around each other, as you see here, and were seen merging about 1.3 billion light years away from Earth. And notice as they merge, you can see the light from behind these black holes bending and lensing, and that's how the event progressed. And because of this in spiral and merger, as the two black holes came closer and closer to each other, they lost energy, which was propagated out as ripples in space-time, which is what we call gravitational waves, and they traveled towards Earth for all of those 1.3 billion years and were finally picked up by humans many years later. So what are these ripples in space-time and where did they come from? How did we learn about them? So they are actually the propagating solutions of Einstein's equations, which is what I have briefly shown here. So don't worry about the math too much. Einstein's equations were propounded by him back in the year 1915, almost exactly 100 years before they were actually observed by us. And in the words of John Wheeler, they basically present to us the idea that Mass, or rather energy and momentum, tells space-time how to curve, whereas space-time tells matter or energy momentum how to move. So these gravitational waves basically have two different modes of vibration. There are two different ways in which they can perturb space-time. And this is usually visualized using the concept of a set of beads on a ring. So we try to imagine how the two different modes of the gravitational wave would disturb such a ring of beads. And that is what I have tried to show here. So the plus polarization, or the plus mode of the gravitational waves, basically stretches and squeezes such a ring of beads in the basically the orthogonal directions, somewhat like in the direction of x and y axes. Whereas the cross polarization, pretty much like the name suggests, does the same perturbing but in the diagonal directions. So it also stretches and squeezes. So again, just to illustrate that, I wanted to show you some graphics straight out of Google. So what you have going on here is the plus and the cross polarizations perturbing that same ring of beads, and this is how we visualize what these modes do to space-time in general. So what does that mean for us? So we people on Earth, all these years that we have been surviving on Earth, a lot of gravitational waves could have been passing through us this whole time. And they would have been stretching and squeezing us pretty much like this. But why did nothing happen to us? Because it is a minuscule effect. So if you take the strain, which in other words is the change in length over length of something which is being stretched and squeezed, then you would come up with a ratio which is of the order of 10 raised to the power minus 23. So just to give you an idea, the size of an atomic nucleus is 10 to the minus 15 meter. So this is a really, really small effect, and hence we do not experience it in our everyday lives. But what this also means that we would have to come up with or construct a detector or a machine which is really that accurate, that can measure an effect which is this small. And that is where the challenge or the struggle was when it came to building a gravitational wave detector. So, and as humans who are determined to succeed, we did build such a detector, and this is a schematic representation of the Laser Interferometer Gravitational Wave Observatories, or LIGO. So what do we have in it? It is an enhanced Michelson interferometer. So it basically contains a laser source, and then the light from the laser is split by a beam splitting mirror, and then the two split beams travel in two perpendicular arms which are about 2 miles or 4 kilometers long each, and then they are reflected back from mirrors that are placed at the ends of those arms. These reflected beams interfere again at the beam splitter and create an interference pattern, and then this pattern is what is detected by the photodetector, which basically converts light into electrical signal, and that is what we have as a signal. So how does this entire process work? So for that I have another movie for you. So let's see what's happening. So we have a laser source, light from it is being split, reflected back, and it enters the detector. So in the default configuration of the detector, what happens is, let me just wait for a second for the video to catch up. Okay, so the reflected beams in the default configuration, they basically interfere destructively. The beams are out of phase and no light escapes into the detector. And what happens in presence of a gravitational waves is that there's a differential change in arm length, because of which the interference of the two reflected beams is not that out of phase anymore, and light starts to leak into the detector, which is then recorded as a signal. Okay, so we have two of these detectors in the US, which is where they were first built. So one of them is in Livingston in Louisiana, and the other one is in Hanford in Washington. And a gravitational wave would take about 10 milliseconds to travel between them. So that's the story about US. But ever since, we have a few more detectors being planned and some of them already operational. So we have a newly operational detector called Virgo, or Advanced Virgo, which is in Pisa in Italy. So that's the European chapter of LIGO. Then we have an upcoming detector called Kagra, which is going to be in Japan, and it's going to be operational pretty soon, from what it sounds like. And then we have the planned LIGO India detector, which will also be operational in the future. So this slide basically gives you a list of all the institutions from all over the world that are a part of the LIGO Virgo collaboration. But this is a slide that reflects the list back when the first gravitational wave was observed in the year 2015, right after that. This list is so big now, I couldn't find a good enough, well-resolved enough picture to fit into one slide. So what I can say is we have institutions from 80 different countries all over the world taking part in the collaboration now, and the number of members is above 1,000. So I wanted to put this picture in. This was taken again after the discovery of the first gravitational wave. So this is the group just at my previous institution, that is University of Wisconsin-Milwaukee. So this is the group that worked on the analysis of data for the very first observation of gravitational waves. And this is just the group at one specific institution. So each of those institutions that I showed in the earlier slide would have groups like this. And behind us, what you can see is the most important member of our group. It is a supercomputer cluster, which is called NEMO, and we have about 8 such supercomputer clusters that LIGO uses to process the terabytes of data that we collect from these detectors. Okay, so, oh wow. Yeah, sorry, the slides may look a little formatted weird because I made them on a Mac and this is a different computer. But okay, I'll do my best to explain. So this is a picture of the signal that was observed from that very first event. And this was what was observed in the Livingston detector. So we are basically plotting the strain signal versus time. And you can see it lasts only a few milliseconds. So this is a comparison between what was observed in the two different detectors, and you can see they match very well. So not only do they match amongst each other, this slide shows us that they also match the type of signals we predict using numerical relativity and general relativity for such systems. So for instance, in the very first panel, you see the detector signal, and behind that in yellow, you see the predicted signal. And so we find a pretty good match for both detectors. And then when we adjust for that inter-site wave propagation time, the two signals from the two detectors also showed us a good match, making us believe that it is a real signal and not an artifact of noise. So I told you that in the presence of a gravitational wave, we are going to see a signal. But what happens otherwise? Does the detector remain quiet? Unfortunately, no. And I'm going to tell you why. It's because we are trying to measure these really, really small vibrations. But what are these detectors exposed to? Because they are terrestrial, they are on the ground, they're exposed to all sorts of vibrations, all sorts of noise sources, coming from vehicles on the street, coming from a train track nearby, coming from weed blowing in the air and slapping across over the walls of the tunnels of the detector, and all sorts of other things, lightning, thunder. They are all reasons for noise in the detector. So there is a lot of noise, and our signals are buried very deep in the noise. So I'm going to show you a video that will help you appreciate that. So this is basically a frequency versus time plot of the signal that we just saw. So you will see that the frequency goes up as the black holes merge. So there's a sharp rise in frequency and it will sound like a whoop sound to you. So just try and listen for that. In this video, you will not just be able to see the signal, but you will also be able to hear it. So the frequency of these signals is within our audible range, so you can hear it. But this video has two parts. Initially, you hear the sound buried in noise, so you can hardly make out. And in the second part of the video, they amplify the actual signal artificially so that you can hear it better. So let's try this. By the way, do you have sound? Yeah.
So essentially, this is a measurement of length that you have made, kept raised to -24.
It
Is
is.
that what you, when you talk about strain?
We are finding the difference in, we are finding this, the distortion or the difference. So it's not, we are not literally measuring the length, we are finding the distortion that the wave creates. So that 10 to the -23 that we measure is actually proportional to the distortion in the arm lengths because of the passing. Yeah, sorry, I'll stop this for a second. Yeah, because of the passing gravitational wave, and that is proportional to the amplitude of the wave that is passing. So what we're really interested in doing is finding out the amplitude of the gravitational wave that is passing through the detectors. So as I was saying, so initially, yeah, let's get back to the beginning. So yeah, in the second part you can hear the sound clearer, and it sounds like the chirping of a bird, and this is the typical signal we expect from compact objects like black hole binaries or neutron star binaries. Binary just means a pair. So a pair of black holes or a pair of neutron stars merging would show us a signal that looks like this, that rise sharply in frequency over a few milliseconds or seconds. And then this chirping sound is hence just called chirp. And we call this signal a chirp signal. So yeah. As I said, the first event that we observed originated from the merging of two black holes that was 1.3 billion light years away. So if we are seeing them now, the event actually happened 1.3 billion years ago. And what was happening on Earth at that point of time? Well, not much. Blue-green algae were beginning to be formed, and single cellular lives were just beginning to evolve. And that's when that collision happened, and the gravitational waves from it traveled for all of these years to be picked up by humans that had evolved on planet Earth by then. So I feel like that's a very deep statement. That's a very beautiful concept, that the wave traveled for all these years. By then, humans had evolved and built a detector to actually observe it. So let us take a brief look at the timeline of events that we are talking, our history of looking at the universe. This is definitely not a complete history. There were people doing astronomy before that, but we start with Galileo. So he invented the modern telescope, and then in 1916, Einstein first propounded the theory of general relativity. And then in the 70s, this man called Kip Thorne, who's pictured here, started to look at the possibility of building gravitational wave detectors. And then in the early 90s, they actually made a proposal to the National Science Foundation in the US. And it was rejected a few times before they were finally convinced that an effect this small could actually be measured, and it was worth spending billions of dollars on. And then finally construction began in the mid-90s, and then it was completed in the early 2000s. Observations began, but we saw nothing. So they realized we needed upgrades, and that started in the year 2010. And then from 2015, a new set of observation runs began. And almost immediately, we saw our first ever detection of gravitational waves. And this detection was important not just because it was the first proof of concept of Einstein's direct proof of concept of Einstein's theory of relativity, which gave rise to the concept of gravitational waves, but it was also the first time that we were observing a black hole pretty directly. And so because of this feat, the Nobel Prize in physics for the year 2017 went to the three propounders of LIGO, namely Kip Thorne, who worked mostly from the theoretical side, Rainer Weiss, who mostly did a lot of the experimental work, and then Barry Barish. So, besides the Nobel Prize, the members of the collaboration who were involved in studying and doing all of the work involved with the publication of the discovery paper were given other recognitions, like the Fundamental Breakthrough Prize in Physics and also the Gruber Cosmology Award. And so we received all those awards and it was all fun, but that's not all. Recognitions are great and we are very grateful for those. But what is more important is the knowledge that we gained from this discovery and the discovery and detection of other black holes and neutron stars after that, ever since. So we'll just take a quick look at the things that we have seen ever since and how that has increased our knowledge of these compact objects. So to elucidate that, I added this cartoon. So this basically helps us compare the extra black holes that we saw with the help of LIGO versus what we had before, what we were already observing before the era of LIGO. So the first observing run of LIGO went from September 2015 to January 2016. So in just this period of time, the black holes that were observed using LIGO is what is shown in blue here. And on the vertical axis of this cartoon is the masses of these objects in terms of the mass of our sun, so in solar masses. There is nothing on the x-axis. So this is the very first event that was observed. It's two smaller black holes coalescing to form a larger one. And these are the other two events that were observed eventually during that very first observing period. And here's a set of black holes that were known from before the era of LIGO using just X-ray studies. And if you notice that they are of much smaller masses than the ones that were observed using LIGO. So we were now beginning to observe objects that are close to like 30-40 solar mass, and they were fusing, they were merging to form much heavier black holes of 60-70. So before the era of LIGO, it was not even known to us that if black holes this massive could actually exist. So as you can see, we were now probing deeper into space and observing much bigger objects. So what happened at the end of the second observation run? That same picture stands thus. So what you can appreciate is we have observed many more black holes, which is again shown in blue, using LIGO. Namely, we have 10 confirmed observations of binary black holes coalescing. Not only that, we also observed a new object that we had not before in the first observation run. And so what happened is we also saw two neutron stars colliding using LIGO. And this, in yellow, what you see here in this diagram are the neutron stars that were seen before, just using astronomy. So neutron stars are these really compact objects. They're really compact stars which have the density of the order of that of an atomic nucleus, and their size is really small compared to that. So it would be about, for instance, a neutron star could be as big as Mumbai and not more. So that is how small and compact these objects are. So they also produce gravitational waves when they orbit around each other, and they can be seen using LIGO too. And that was something that LIGO did see. Now this event was particularly important because not only could it be seen using gravitational waves, but it could also be seen by using telescopes by astronomers. So this was the first time we were able to actually corroborate a gravitational wave event using electromagnetic waves, that is using telescopes as well. And both kinds of looking at the same, both channels of looking at the same event actually increased our plethora of knowledge about everything that happened during and after that collision. So we'll take a brief look at that. So I have a video here that will show you what that collision looked like. This is a simulation, this is not photography. So I'll try and explain as we go. So the two neutron stars were seen to coalesce around each other and orbit around each other and then coalesce. And what you see in those blue arcs is basically a representation of the gravitational waves. Gravitational waves don't have color, it's how the simulation shows it. And then after the coalescence, you see a lot of things happening. So in brief, what happens is initially there is a gamma ray burst, then a lot of matter is ejected out in a very violent explosion called a kilonova. And then there is the emission of a lot of different types of electromagnetic waves, beginning from ultraviolet, optical to infrared. And then eventually the remnant becomes an X-ray source. And this is what happens over 9 days right after the collision. And then in the long term, this can become a source of radio waves. So for many days, weeks, months after the event, astronomers from all over the world were following up, were observing this event, and the gravitational wave emitted was in the first few seconds, and that was what was observed by LIGO. So this was the first time that an event was observed in matter, which is what you see here, matter being thrown out, and then also in gravitational waves, so much so that it could be corroborated by both parties. Okay, so that is what I elucidate here again. So here you see the coalescence in matter. The different shades represent the different densities of matter. And on the other panel, you see the event in the ripples in space-time or in the gravitational waves that start to get emitted. So you see that as the two stars get close to each other, they get deformed tidally, and then they finally merge. So yeah, this slide basically shows us the follow-up team, and it is spread all over the world. So the three yellow dots are the gravitational scientists, the gravitational wave physicists who were looking at the event using gravitational waves. And in the light blue are the astronomers from all over the world and from space, like, well, telescopes really, not necessarily human astronomers, who were following up and looking at this event for months later. So let me talk about how we find out in which direction that the gravitational wave came from. So basically what you see here is a sphere which represents the observable universe from Earth. And these colorful patches are regions of uncertainty around our idea of where the gravitational wave actually came from. And so each of these are some of the different events that we have observed so far. And the naming convention is GW represents gravitational waves. The first two digits are the year, followed by month and date of observation. So if you look at some of the older events in the year 2017, for instance, this is an event from 4th January in the year 2017. It's a huge patch in the sky, which is almost like saying we have very little idea where this came from. But as you progress through the year, for instance, for this event, which was from 17th August in the year 2017, this is actually the binary neutron star detection also. You see that the size of that patch has reduced down to a really small space in sky. So to put some numbers to words, this was an improvement of about a factor of 6. This was about 190 square degrees, and that was reduced to just around 30 square degrees in the sky. And why did this happen over time? Well, because from the August of the year 2017, a third detector joined the network. And this was the European detector that I talked about earlier, called Virgo. So with the third detector joining in, our idea about localizing the origin of these gravitational waves highly improved. So this is a video that just shows how the localization was kind of done. So initially we had satellites like Fermi and Integral trying to locate the origin of the binary neutron star event. And then when you put in LIGO's contribution, which will appear in a second, what happened? Oh yeah. So we narrow things down a little more. And then finally, with Virgo joining in, we have a more precise idea of where the localization is. And we know that the event came from a galaxy called NGC 4993. That's where the video is zooming in now. So the astronomers and the gravitational wave physicists working together helped us locate the source of this gravitational wave better. So this is actually a slide that talks about how much LIGO India will contribute to this specific scene of localization. So this is actually another diagram that shows us the observable sky. This gray patch that you see is actually the area of uncertainty around the localization of the very first observed gravitational wave from the September 14th from 2015. And this measures about 600 square degrees in the sky. And the idea is when LIGO India joins in, there's going to be a factor of about 100 improvement, and the uncertainty is going to be that small. That's the that's how they are foretelling it. And I just added a picture of the site that has been proposed at Hingoli, where LIGO India is going to be set up. But you will probably have more panelists who will talk about this in greater details. So I'm going to shift gears a little bit now and talk a little bit about the search for such compact objects, because that's the area I majorly work in. So compact objects include the binary neutron stars and the black holes, these heavy massive objects. And I'll talk about how exactly we use the data to search for these objects. So there are two major ways in which you could be searching through the data. So one of them is by using templates of what we expect, which is a process known as filtering, or it's actually a model search rather, where you have a model for the kind of gravitational wave that you expect from such compact objects, and then you match the data against this template and you look for a high level of correspondence. So when you do have a high level of correspondence, you know that this could be actually a signal. So that's a model search. But there are also unmodeled searches where you assume nothing about the form of the gravitational wave, and you just go ahead and correlate data from the different detectors and look for an excess in the power. So I specialize in the area of using templates to look for gravitational waves. So what does that really look like? So this is an example, random example of a template of a gravitational wave. So the two compact objects are coalescing, and this is where the merger is. So this is what we are trying to look for in this jungle called data. So if you look at this is like highly fluctuating everywhere, and I don't know how visible this is at people at the back or something, but the order here is around 10 to the minus 19, whereas here it is 10 to the minus 10. So it's almost an order of 9 difference, and so we are almost we are looking for this, and this would be a really small blip in here. So it's talk about looking for needle in a haystack. So what we do for that is use a whole collection of templates. That is what I show in this slide. So this is basically the search space for our template-based searches that was used during the second observation run. And I have projected that on the component mass plane of these objects. So M1 here on the x-axis is the heavier of the two masses that are spiraling around each other, and M2 is the lighter of the two masses. So these are your black holes or binary neutron stars, and then each of the points in this diagram represent one such system that we may expect gravitational waves from. And so each of these points is also a template in our search that we use. So this collection of templates is together called a bank. And in this specific bank, we had around 700,000 templates. So in the lower mass region of this bank, going between a total mass of 2 to 100 solar masses, we have what we call stellar mass binaries. And this includes neutron star pairs or neutron star binaries, black hole and neutron star combinations as well. And then we have our usual binary black holes like we have seen. And then above 100 solar masses, we have heavier, more massive systems, and we call them intermediate mass binary black holes. And they have total masses ranging between 100 solar mass to as high as 10 to the 5 solar masses. But our search ends at a total of 400 solar masses. That's what we are sensitive to right now. And they are called intermediate because they lie somewhere between our usual vanilla stellar mass binary systems and the supermassive black holes. So they are basically just heavy mass objects. And so those are the type of things we are searching. So just to give an idea about what's going on right now with LIGO. So the third observing period of LIGO started on the 1st of April in 2019, so it's been about 2 months. And the interesting part is we have seen about 13 different gravitational wave candidates. And so including the first and the second observing period, we had a total of 11 candidates. In fact, 11 proved gravitational wave sources. But now just within 2 months, we have 13 candidates. So that's a lot. So what does candidates really mean? It means we have seen some deviations in our data which convince us that there could be a gravitational wave. We are not sure yet. We are not sure what kind of sources they come from, and we are doing all sorts of investigations to try to figure out if they are really gravitational waves, and if so, what kind of sources they come from, whether they are black holes, binary neutron stars, or neutron star black hole binaries. And so all of that calculation, all of those investigations are taking, basically is burning our night lamp, and it's raining gravitational wave candidates, and we are sleepless, so send coffee. So what can we expect then at the end of the third observing run? So as you saw, the earlier observing periods were about ranging from 4 to 6 months. This time we are going to have a longer observation period, so it's going to run for the rest of the year and probably a little into next year as well. And so we expect to observe a lot more events than we did before. And not only that, we also expect to observe a few new things that we have not seen so far. So far we've only seen binary black holes, and we have seen a binary neutron star. But we have not seen these heavy mass black holes or the IMBHs, nor have we seen neutron star black hole pairs. So we expect to see some of these objects too. And then with these observations, we are going to be able to do more science than what we have been doing in the past. We will get a clearer idea about the formation of these objects. We'll be able to constrain astrophysical theories that try to understand how these objects were formed and answer other astrophysical questions. So yeah, in the end, I'd like to say that I'd like to end with this quotation from Rainer Weiss, which says that we can actually begin to see the whole universe now in black holes. And this is something I personally identify with, because I did my PhD and I'm doing my present research just about in the era when we went from having zero observations, knowing nothing about whether black holes actually exist, to knowing they exist and understanding how they are formed. So that's a big leap in our understanding of these objects, and that has happened over an expanse of about 5 to 6 years. So we are truly living in the era of doing science with black holes. Thank you. I don't have much else.
Thanks, Devnanvin. So,
I have a set of questions, yes, but they are not very multiple choice. They are intended to make you think and answer.
So if you have any questions, we can ask them now.
So I also have a set of questions if you want.
Yeah. And otherwise, we can just
identify like when the we get from the coalition of the binary stars or from the black holes. How do we identify like whether it's a star coalition or it's a black hole coalition?
Yeah, that's a very good question. They all look different from each other. So, for the less massive objects, we expect the signal to be much longer. And for the more massive objects, for instance, the IMPHs, we are going to see very few signals in our sensitive band. So we are going to see a signal that looks different. So, for instance, the binary neutron star coalescence that we saw, the signal lasts for a few seconds. Whereas for the black hole signal that I showed you, it's a few milliseconds. So the lengths are different, the shapes are different as well. Yes.
Spinning direction of two stars can affect causing of spinning direction.
Spinning direction, yes, it can. It can change the time it takes to coalesce. We'll get a different type of a waveform. So right now the templates that we have, they are all either aligned spin or anti-aligned spin templates. But if you don't have the spins aligned, then you can have other interesting effects, which we, will be exploring in the future. We'll have precision. Yes.
Why merge in a spiral manner? Why they merge in a spiral manner? Like they can have a head-on collision.
So these are objects that were in orbit around each other because of various dynamical reasons. So these black holes or neutron stars, they fall into each other's gravitational potential and then stay in orbit for ages, and then they start to coalesce because they lose energy in the form of gravitational waves, and that is why they are orbiting. So why did they get into orbit in the first place depends on how they originated from the progenitor stars. By progenitor, I mean the stars they originated from. And there are various dynamics like kicks and stuff like that, which causes these objects to come close to each other and then fall into orbit. So whenever two heavy objects out there in the universe come close to each other, they are gravitationally in each other's sort of gravitational potential, and then they fall into an orbit, like the Earth's sun, Earth, moon systems.
You said you use laser to find out gravitational wave. So which type of laser do you use? Infrared, ultraviolet, or which spectrum, wavelength of the laser lines?
Wavelength of the laser light, I don't know off the top of my head. But if you
instrumentation questions, we can have them directed to Shivraj, because here who actually works on the detector itself.
1064 nanometer.
Okay.
I was interested in the timelines. You said these are candidates. That you have the candidates for a gravitational wave potential or developing. That means the recording happens continuously and you analyze the data thereafter and then find it. It's not something that you see as it is happening, is it?
No, we do. We have two different types of searches. We have an online search, which is more of an immediate, like you look at the data and you have enough background collected to know if you have a signal or not. So there's an online system that collects data and can determine whether you have a detection, at least at the primary level, within a few seconds. But then there is an offline, deeper archival search, which actually collects, which is done later, and then that has the advantage of having collected more data, so it has a better estimation of the noise in the detector, better estimation of the background, and is going to give us a more realistic picture. So we do have an online immediate way of looking at things as well as a later deeper search.
So when you talked about the various phases of the detection process, you said the one worked for about 3 months, and then the second stage happened for listening, and the third stage, which we're going to get into now, is going to happen for more than a year. What are the limitations that created these
stages
to stop these short periods, and what have you improved that goes no longer?
Yeah, so basically, it's the length of time during which we can commission the instrument without having to undergo some maintenance work. So, when we do some maintenance work, we improve the isolation of the instrument from the ground, from the noise sources. We improve for instance, the mirrors, the end mirrors are suspended by very complicated mechanisms. We improve that. Yeah, again, an instrumentation guy can give you more details. But yes, it is instrumentation improvements.
And how many were found online and how many were found archived?
Okay,
I mean,
yeah.
curiosity.
So at least 5 of them were definitely found by the online. 5 to 7 of them were found by the online search. About 2 or 3 were not found by the online searches immediately, but were found in the archival searches later on.
And these things you said last for just a millisecond. So
Yes.
does it actually also in 1.5 billion years it lasted for a millisecond, or it's something that you observe in a period of 1.5 milliseconds which could have happened over a longer span?
No, they did take only just that much time to coalesce. Yes, these are like the bigger the object, the faster, the bigger the gravitational field, and the faster they fall into each other. So, I mean, yeah, how fast they will coalesce depends on the mass of the initial systems. Yeah.
But it's the order of
Yeah, it's the same. Yeah, we are not seeing a different time interval now.
It's 1.3 billion light years.
A billion light years. I mean, that's the distance, and then so light travels like 1 light year in a year. So we are seeing it 1.3 billion years later because it is so far away.
Is there any criteria for selection and iteration of LIGO?
Sorry, could you please repeat the question?
Is there any criteria for selection of LIGO? Place to install.
Oh, okay, yeah. So, yeah, that's a good question too. So, I think the biggest criteria is finding a place that is seismically quiet. That is where we are not going to have too many earthquakes. And, well, we don't want earthquakes at all. Not too many, we just don't want earthquakes. And then we also don't want disturbances from human activity like city, buses, cars, all of that. And so, as we want an area that is as quiet as possible, it's going to have fewer humans interacting with the system. So, for instance, he lived on site, and he's going to tell you that around you were in Livingston, that even cars have to follow certain instructions when entering and leaving the facility, and so on.
Yes, mostly you look at like how generally cycling like quiet throughout the year. Did you come up? No, so generally quiet, it has to be quiet throughout the year, and also not as I said, not many people living are nearby. And third one is also like how we can access the site. So accessibility is also important, and how much feedback we get from the local population and get support from the local population. Those can also decide which place we choose for our site.
Yeah.
Then what about the site in Japan?
What about the site in Japan? Like, what's your specific question?
Yeah, like
Seismic. Okay, so the site in Japan has. Oh, okay, because you think it's an earthquake-prone zone. So they have a cryogenic facility. So they have the whole system is underground, and it is in tunnels that are going to be cryogenically cooled, and it's going to have more developed isolation systems from what we know. So the moment you cool things down, you might have read about Brownian motion at some point in life. So the things stop jiggling as much, and then that just improves basically reduces the possibility of having noise in your data.
My finding position is a linear system for means cohesion position.
Why is it important? Okay, that is a very deep question actually. So it is important because we at the end of the day want to understand the distribution of these objects, these astrophysical objects like the binary neutron stars, black holes, and so on. We want to understand how these objects are distributed in the universe around us. So, why is that important? Because the distribution of these objects depends on how they are formed and how they evolve, how these stars evolve. So, if we find a specific type of distribution, then that would mean a certain formation mechanism is preferred over another. So, astrophysicists so far have been running simulations and theoretically have been trying to predict how these objects were formed. And as a result of those predictions, we think there are several different possible scenarios of distribution of these objects. Now, when we actually go and observe these things, this is like the experiment. This is what helps us constrain those theories. So, depending on what we see, we give a feedback to the physicists, so to speak, and say that, okay, so what you said worked, what you said did not work, what you said did not work. So, that's kind of the work we are doing. So, that is why the distribution is important.
I think maybe we can have questions from Dave Nandini now.
Okay.
To you. There are gifts to be won, so try to answer them.
So, me a lot of questions and I have answered them. So, in light of that, these questions may be really easy, but I think it's still a good practice in helping you remember what you heard. So, what do you think is the speed of propagation of gravitational waves? So, raise hands so that. How do we choose this?
Whoever we want.
Whoever I want?
Yes.
Okay, I think you raise first. So. Yeah, what is it?
3 to 10 to the power 8.
Did you say kilometers? Okay, so I don't know how you determine. He was right in part of the question. But
Okay,
not
we are
wrong.
good. We are good.
Okay. So, okay, so this is a question about one of the simulations you saw, the very first simulation you saw when the two black holes were merging. So, the question is, I told you that you saw that there was this ring that was appearing around these black holes. So, what phenomena is that due to? Please raise hands. Okay.
Bending of light due to gravity.
Okay, so can anyone give me a one-word answer to that?
Lens,
Let's
gravitation.
Okay, so I guess the person with the more accurate answer.
Gravitational lensing it is.
Yeah.
Very good. We'll just have the prizes at the end of.
Oh, you have tried.
Yes.
Okay, so I have this other question, and that is, what would happen if a gravitational wave passed through you?
You wouldn't feel stretched in.
Okay, I think she said nothing first. Yeah.
Okay.
So, why do we need a network of detectors? Yes.
to minimize the possibilities, when you had less number of detectors, you had a larger number of possibilities throughout the sky.
Okay,
So you
possibilities of what? Let me just cut you.
want, possibilities where it's like inverse GPS. Yeah.
Okay, you're getting close. Just
Yeah, we use 3 satellites in the sky to focus a point. Yeah, you need to focus.
yeah, I think
a
that's the
point in
general
sky.
idea. Yeah, it's better localization. So yeah. Okay, so if we could find the place and wanted to build a detector in Mumbai, what would be the biggest challenge? No, I already said if we found the place. Well, traffic. Well, for the just in terms of detecting things,
The waves,
I think I heard some people say the answer.
It's the noise purity. For example,
Yeah, so all of those are actually pieces of the right answer, but the general answer is noise. I think you said that. So yeah, there would be waves from the sea, there's traffic, there's all of these factors contributing to noise. So
Better not build it in Mumbai, I tell you.
no. So how many different types of compact objects have you heard about today in this talk?
Black holes and neutron stars.
There were more.
I am being
Yes. So actually, it's both are actually correct in some sense, because IMBHs are just larger black holes. So okay, this is a true or false question. So in the absence of gravitational waves, data from the detector should look like a flat line. Yes or no? False. Yes. Because of noise, you're going to see a lot of other things. So okay, so a partnership between the astronomers and gravitational wave physicists is required to understand which type of compact objects better, or rather which type of compact object binaries better, and there could be more than one.
Neutron star, because it has pulsars and both collaborate with each other.
Yes, but if I ask the question of which types of binaries, so neutron star binaries as well as neutron star and black hole binaries, those can also be observed by them. But I guess I did not directly address that during the talk. So okay, here's another true and false question, and this is the last one. So you heard about a bunch of different detectors. Some are built, some are being built. Would you expect the noise in two different detectors to be the same? False, yes. Because there are different factors contributing to it, and it's different in different locations. Okay, so I think that's all I have.
Okay, very good. Let's thank our speaker, Dr. Devnandini Mukherjee.
Thank you.
I now request all the people who gave the right answers to please come before the stage so that we can hand you over the prizes.